Hi, I'm Raj. I'm a PhD candidate at Georgia Tech, and I'm going to talk to you about how to avoid being eaten by a Grue, structured exploration strategies for textual worlds. Okay, so people affect change in the world all the time using natural language, right? So a solid chunk of our communication is grounded in real-world actions. Now, think about using that kind of communication to help train agents that operate on language. So what if we could have the same kind of success with these that we do with all these, game agents that you see running around everywhere? Agents that operate on language, you say. Now, where have we seen these before? Right, so they're everywhere now, right? And a lot of these agents have to operate in situations where they need to perform goal-oriented language generation tasks without any of this sort of language grounding, right? So now when you say goal-oriented, reinforcement learning is the first thing that comes to mind. And yet, human interaction for RL is quite costly, right? And as a direct consequence of this, situated language learning is not something that's particularly well studied. So the question now becomes, does there exist a platform on which we can more easily simulate communication grounded in real-world actions? Turns out the answer is yes. So introducing text adventures or interactive fiction games. So text adventures are sort of different from your typical video games in that they're structured as puzzles or long quests in which all your interaction with the world is through textual natural language, right? So what you're seeing on the screen here is an example of one of the earliest, most popular text games, Zork. So when you first enter the world of Zork, you see a description of the world around you. You're standing in a field west of a White House. There's a mailbox there. Given this, you can type in what you want to do, open a mailbox, and, opening the mailbox reveals a leaflet, so that's the response that you get from the game, so on and so forth. So, this game consists of, hundreds of locations. So this is a map of the world of Zork. So there's, tons of locations, characters, objects for you to interact with as you make your way through this quest. Okay, so there's two primary challenges associated with dealing with text games. I'm going to go briefly into them now. So the first is that of partial observability. So this is really the question of, how can agents better represent the state of the game world, right? So like I said earlier, all an agent receives is this description of what it sees in the world around it. So like a description that can potentially be incomplete, right? So these, interactive fiction games, they have tens to hundreds of locations, unique descriptions, characters, objects, whatnot, right? So, how can the agent represent all of this? So this is really almost like a textual slam question where you're learning a map of the world while you're exploring it. So furthermore, a game like Zork requires you to generate sort of at least 4 work actions, right? So you add this to even a fairly modest vocabulary set of around 700, you still get 240 billion possible actions that you can take in every step. So how is it that we can adapt RL algorithms, things that are generally designed for either small, discrete action spaces or continuous action spaces to handle this sort of ridiculously huge space, right? So all these approaches also have, these sort of fairly simple exploration mechanisms, right? So epsilon greedy, Boltzmann, whatever. And it turns out these don't really get us anywhere close to being able to solve these games. So what we really need is we need smarter exploration that thinks about the structure of the underlying MDP and that exploits it. Okay, so I said the magic word, I said structure, and so here's that structure. So text games are, long puzzles or quests, like I said, and they can be represented as a directed acyclic graph of the dependencies that one needs to satisfy in order to finish the game. So what you're looking at here is such a dependency DAG for the game of Zork. So now, if you look a little bit closer at this dependency graph, right? So this set of dependencies, what are the locations we need to be in? What are the kinds of things we need to have within our inventory and so on to pick up these rewards? We're going to start to see patterns here. And we're going to start to see some states where, regardless of the path that we took to get to that particular state, any agent must go through it in order to continue collecting future rewards. And this is basically the intuitive definition behind what we're going to call a bottleneck state from here on out. So this brings us to the sort of like motivating hypothesis of this paper and sort of on why current RL agents are stumped by text games in general. It's really because it's this combination of partial observability and this combinatorially sized action space that the bottlenecks are hard to find and they're even harder to surpass, right? So they're really just like one tiny state in this like sea of like ungodly number of states, and they require a very specific sequence of actions to surpass. Okay, so with that in mind, we're going to go back to this DAG and see if we can formally define what we actually mean by a bottleneck state. So this is a definition that we came up with, and we're going to use this through the rest of this talk to sort of implicitly do structured exploration. So this definition basically is just saying, this is the set of all possible states that belong to a level in this DAG when topologically sorted, such that there's only one vertex, and that there exists, some state with a non-zero reward that exists on this level with one vertex. So this is just like a formal way of stating what I intuitively told you before. Okay, so how are we going to use this to do structured exploration? Well, this is how. So this is the entire structured exploration algorithm on which the rest of this talk is going to be based. But I'm not going to make you digest pseudocode, so I'll just condense this into words. So there's going to be roughly 2 phases of structured exploration based on what we've seen so far. So the first bit of this is we're going to detect bottlenecks by using this piece of intuition that bottlenecks tend to happen when agents stop learning new information about the world, right? We're going to see how to do this, and once we've detected bottlenecks, we're going to figure out how we can stack policies that take us from one bottleneck to the next, and basically how to surpass the bottlenecks themselves. Okay, so the first bit of this, getting right into it, the secret sauce for how we're going to figure out where agents stop, learning information about the world is by representing the world as a knowledge graph. So now knowledge graphs are sort of this like very intuitive way of representing the world of a text game. So, they're easy to understand, they give us structured memory aids, they've been shown to help in a lot of the subproblems of text games so far. And, actually people have been using these for quite some time now. So like what you're looking at on the screen is a hand-drawn map of the world of Sork. So the knowledge graphs themselves are this, set of subject relation object triples that the agent builds up as it explores the world, so it extracts it from the descriptions that it sees in the world. And there's sort of 2 ways of doing this. So the current sort of way of doing this is the KGA2C. It's this rules-based approach, prior work, and all this really is you're just using an off-the-shelf, information extraction system added to some hand authoring to extract the kinds of information that you need. And on the right here is, what we're doing in this paper is to frame it as a question answering problem. So this question answering problem is basically now where the agent is intrinsically motivated to ask questions about the world. And then it answers the questions about the world that give it, sort of like more information to sort of help it better understand the world. And we're going to see a little bit later that, this helps us generalize better and provides better sample efficiency. And of course, we need something to train this agent. So sort of like also accompanying this work is this data set of over 200,000 question answer pairs from over 30 games to help train such a question answering system. Okay, so this is what this QBERT system looks like, and the general idea here, like I said, is that the agent builds a graph using, this question answering model as it goes along. So what does this actually look like? So the agent first receives a description, like I said, of the world, and then it sends this description to this question answering, like querying model, right? So we then query this model using this description as context and questions such as where am I located, what's here, what do I have? And this model's responsibility is basically to highlight the span within the description that best answers that particular question. So when you have it, you basically have this set of like important vertices that you have in this graph, and we can then combine it with the graph that we've had at the previous step in order to get, a full knowledge graph of what the world looks like, something like what you see on the screen. So this knowledge graph has, information regarding, the locations of the agent, surrounding objects, the inventory objects, attributes, so on and so forth. So the bits after this is basically just consisting of trying to crunch this graph down into an n-dimensional vector using like an RGCN for the graph and a recurrent text encoder for like all the text description bits, and then passing that on to the actor, which basically, conditioned on this n-dimensional vector representation, it then outputs an action and a value for, what it's supposed to do in that particular state. So, the rest of the training is done via A2C, the Advantage Actor Critic. It's a well-known RL algorithm, that with like some tweaks. So I'll skip the details of the training so you can read the paper for more of that. So the sort of first evaluation bit here is to look at how accurate the graphs are when comparing the rules-based method to sort of the learned QA approach. And there's no real surprises here, right? The QBERT basically improved significantly on prior methods in terms of having better quality graphs. And sort of as a consequence of having better quality graphs, we also see here that we have better sample efficiency when using QBERT. So basically what you're looking at is we get to this sort of like max score that we see in the game faster using QBERT with this sort of like learned graph mechanism approach than we have with any of the rules-based approaches so far. Yet the sort of like caveat here is that even though we get to this max score faster, this is still not enough to surpass, the bottlenecks that are seen in this game, and to actually improve on, the overall highest score that we've seen, the previous state of the art. So this brings us to the second bit of structured exploration. So we figured out, how to detect the bottleneck, right? So it's basically the stage that we see like earlier where, our score is plateaued and we're learning no more information about the world. So what happens now, right? So what happens now is that we take the policy that got us to this bottleneck and we start backtracking by restarting exploration from areas explored before the detected bottleneck. And then illustrate this with an example. So, here's the quest tag again that we've seen so far. And in particular, I'm going to use the example of the cellar, the bottleneck that happens at the cellar, right? So now the cellar is dark, and in the dark places of this world lurks the Grue. So the Grue is, one of the first ever monsters created in a computer game. And in order to get past the Grue, what you need to do is you need to take a lamp from your inventory and light it. It seems simple enough, but in fact, this is a bottleneck that no current full action space RL agent has ever been able to surpass. Right? So in terms of the map that we see earlier, so this is what the map looks like. You see the cellar on the right here, and sort of just like remember that the blue arrows are connecting the left and right sides of the map. So the overworld and the underworld of which the cellar is an entrance to. So let's say that you've detected this bottleneck. So there's this dark and spooky Grue in this cellar. It's constantly eating you. What are you going to do about it, right? So here's what we're going to do about it. We're going to basically go to the areas that happened right before we detected this bottleneck, and we're going to systematically explore the areas that are closest to the bottleneck. Right? So we're going to restart exploration from the states there in hopes of finding a way of surpassing the bottleneck. And so this heat map sort of represents how often the states before this bottleneck are visited. Basically, the closer to the bottleneck we are, the more the states are to be explored. And if we do find a way of surpassing it, then the policy that surpasses it is frozen until we get to the next bottleneck down the line. Okay, so this whole system is called the MC Cuber, and we see that for the first time ever, we have RL agents that get past this particular bottleneck. So that's the blue line that we see here. And not just on Zork, but like on a bunch of other games as well. We actually hold state of the art. So on 8 of 9 of the games that we've tested. And another sort of like interesting result here is comparing the blue to the yellow line. So the yellow line is when the bottleneck detection's been taken away. And the key idea here is that this bottleneck detection and backtracking are this sort of like combo package. And you take away either of these pieces and this entire system basically like fails to work. And not just that, it also does much better than, other sort of like fancy similar exploration systems that have been used in things like Atari games and whatnot. So stuff like Go Explore. Okay, so the sort of 3 main takeaways here is that faming knowledge graph construction as question answering leads to higher quality graphs. Better quality graphs lead to better bottleneck detections when an agent stops learning new information. And detecting bottlenecks lets us sort of selectively backtrack through the important parts of the search space in order to surpass them. So the question here is, how do you avoid being eaten by a Grue? The answer is simple, of course. All you need to do is get land. Thank you. So that's all. The paper and the code can be found here, and I can be reached at these locations.